The effect happened before the cause. Not in a thought experiment, not in a philosopher's argument, in a real laboratory with real particles measured by real instruments, the result came in before the experiment was run. Physics confirmed it. The data is unambiguous. And what it implies about the nature of cause and effect, about the most fundamental assumption we make every second of every day, is something most scientists still don't want to say out loud. Causality might be an illusion. I'm Leonard Susskind. I've spent 50 years working at the foundations of physics, quantum mechanics, string theory, the structure of space-time. And the more deeply I've understood these theories, the more uncomfortable I've become with something everyone takes for granted. The idea that causes come before effects, that time flows in one direction, that the past shapes the future and never the other way around. That assumption is built into everything. Every experiment we design, every explanation we give, every story we tell about how the world works. First this happened, then that happened because of it. Cause, effect, sequence, direction. Physics is beginning to suggest this picture is wrong. Not approximately wrong, fundamentally wrong at the level of individual quantum events. And if it's wrong there at the most basic level of reality, then what we call causality may be something we impose on the universe rather than something the universe actually has. Let me show you why. Starting with the experiment that changed everything. In 1964, the physicist John Bell derived a set of mathematical inequalities to answer a question that had divided physicists for 30 years. Are quantum particles secretly carrying hidden information? Or is quantum randomness genuinely fundamental? This debate had deep roots. In 1935, Einstein, Podolsky, and Rosen published the EPR paper. Einstein considered it his most important contribution to quantum theory. Two particles interact and separate. Measure one, and you instantly know the corresponding property of the other, no matter how far apart they are. Einstein's conclusion: either hidden information was already encoded in the particles, or measuring one somehow instantly affected the other at any distance. The second option, spooky action at a distance, violated everything he believed. Influences could not travel faster than light. Causation had to be local. Niels Bohr disagreed. He argued quantum mechanics was complete, and demanding a local hidden variable explanation imposed a classical prejudice onto an irreducibly quantum reality. Both men died without knowing who was right. Bell showed you could settle the question experimentally. The test was run, first by Alan Aspect in 1982, then by increasingly rigorous experiments culminating in loophole-free tests in 2015. The result was decisive. Bell's inequalities were violated. Local hidden variables don't exist. Einstein was wrong. Bohr was right. The spookiness is real. What this means is extraordinary. Take two particles, entangle them, separate them by any distance. Measure one. The other instantly exhibits a correlated property. Not because a signal traveled between them faster than light signals are impossible, not because they pre-agreed on the outcome. Bell's theorem rules that out. They're correlated for no local reason that physics can identify. Now here is where most explanations stop. They say, yes, it's strange, but you can't use entanglement to send information faster than light, so causality is safe. The correlations are real, but useless for signaling. Nothing to worry about. I don't find that satisfying, and here's why. The question isn't just whether you can send a message. The question is what the correlations mean about the structure of causality itself. When two events are correlated without any causal connection between them, without any signal, any shared history that could explain the correlation in ordinary causal terms, then you are forced to choose between two uncomfortable options. Either there is some form of non-local causation, some influence that operates outside the ordinary structure of cause preceding effect in local space-time, Or causality, as we understand it, simply doesn't apply at the quantum level. Both options are radical, and physicists have been arguing about which is less bad for 60 years. But there's something even stranger, something that goes further than entanglement. Retrocausality. In certain interpretations of quantum mechanics, the math works better, more elegantly, more consistently if you allow causal influences to travel backward in time. Not just forward from past to future, but backward from future to past. This isn't fringe physics. It's a serious proposal developed by serious physicists, including Hugh Price, Ken Wharton, and others. The idea is called the two-state vector formalism, or retrocausal quantum mechanics. And it makes exactly the same experimental predictions as standard quantum mechanics, every single one, while treating the future as causally active in determining the present. In this picture, when you measure a quantum particle, it's not just the past preparation of that particle that determines the result. The future measurement setting also contributes. Causation flows from both directions, from past to present and from future to present simultaneously. Does your measurement apparatus's future setting affect the particle before you've decided on that setting? In retrocausal quantum mechanics, yes. In a deeply subtle, non-signaling way that cannot be used for time travel or paradoxes, but yes, the future is causally active. The experiment I mentioned at the beginning, results arriving before the experiment was run, refers to a class of delayed choice experiments first proposed by John Wheeler and subsequently tested many times. Wheeler asked, what if you set up a quantum experiment, let a particle travel through it, and then decide after the particle has already passed through the apparatus whether to measure which path it took or let the paths interfere? The answer quantum mechanics gives, and experiments confirm, is that the particle's past behavior changes depending on your future choice. If you decide to measure which path, the particle behaved as if it took a definite path all along. If you decide to let the paths interfere, the particle behaved as if it went through both paths simultaneously. Your choice, made after the particle already passed through the apparatus, determines what the particle did before you chose. Let me make this even more concrete. In 2007, a French team performed a delayed choice experiment using a beam splitter, a device that can either split a photon into two paths or recombine them. The photon entered the apparatus. It traveled through. Then, after it had already passed through the first beam splitter, the experimenters randomly switched whether a second beam splitter was in place or not. If the second splitter was in place, the photon showed interference wave-like behavior, as if it had traveled both paths. If the splitter was removed, the photon showed particle-like behavior as if it had taken one definite path. The decision was made after the photon was already inside the apparatus. The photon's past behavior depended on a choice made in its future. In 2015, this experiment was scaled up cosmologically. A team used gravitational lensing, the bending of light around a distant galaxy, as the apparatus. Photons from a quasar 9 billion light years away were split by the gravity of an intervening galaxy. The choice of how to measure them was made here on Earth 9 billion years after the photons began their journey. The results were the same. The photons' behavior over 9 billion years of travel was determined by a measurement choice made at the end of their journey. 9 billion years of history, apparently influenced by what we decided to do when the light arrived. Wheeler's delayed choice experiment has confirmed this effect at every scale it has been tested. And what it implies is something that should genuinely unsettle you. The present can reach back and shape the past, at least at the quantum level, in ways that are real, measurable, and reproducible. Now, I want to be careful here. These experiments don't prove retrocausality. There are other interpretations. Many worlds, for example, avoids retrocausality by saying all outcomes happen in different branches. Copenhagen avoids it by refusing to ask what the particle was doing before measurement. But here is what none of the interpretations can avoid. The ordinary classical picture of causality, where causes unambiguously precede effects, where the past determines the future and never the reverse, does not hold at the quantum level. Something is wrong with the classical causal picture. All the serious interpretations agree on this. They just disagree about what to replace it with. Let me now connect this to the block universe, because the two ideas together paint a picture that I find both deeply strange and strangely coherent. In the block universe, the picture that special relativity forces on us past, present, and future all exist simultaneously in a four-dimensional space-time structure. The present doesn't have a privileged reality. The future isn't unwritten. It's already there at its space-time coordinates, as real as the past. If the block universe is correct, then the asymmetry between past and future is not a feature of fundamental physics. It's a thermodynamic feature, a consequence of low entropy initial conditions, not of deep causal structure. The laws of physics themselves are almost perfectly symmetric under time reversal. Run any fundamental physical process backward, and you get another valid physical process. Think about what that means concretely. Film an egg falling and breaking on a kitchen floor. Run the film backward. Shards of shell fly upward. Yolk and white gather themselves. The egg reconstitutes and leaps back into someone's hand. This backward film looks absurd. We instantly recognize it as unnatural. But here is the thing. Every individual molecular collision in that process is time reversible. Each atom bouncing off another atom would look equally valid, running forward or backward. The laws governing those collisions don't distinguish past from future. The irreversibility, the sense that broken eggs don't reassemble, comes entirely from statistics and probability, not from fundamental law. A broken egg represents an astronomically vast number of possible molecular arrangements. An intact egg represents a tiny, specific arrangement. The probability of all those shards spontaneously assembling back into an egg is not zero. It's just so close to zero that it will never happen in the lifetime of the universe. The arrow of time is a statistical arrow, an entropy arrow, not a causal arrow built into the foundations, which means cause preceding effect. The bedrock of every causal story we tell rests on a thermodynamic foundation that is itself contingent. We live near the low entropy end of the universe's history, in a region where entropy increases as time advances. That's why causes come before effects in our experience, because we're embedded in a thermodynamic gradient pointing in one direction. In a universe with a different entropy gradient, or at the fundamental level of individual quantum events where entropy considerations vanish, causality as we understand it has no purchase. In this picture, asking why causes precede effects is like asking why the north end of a compass points north. It's a consequence of where you are and which direction you're facing, not a fundamental feature of the compass itself. Cause preceding effect is a feature of how we experience the four-dimensional structure from inside it, given the thermodynamic gradient we happen to be embedded in. Not a fundamental law, a perspective. Now, I need to address free will, because this is where most people feel the stakes most directly. If causality is not fundamental, if the future can influence the past, if the block universe is real, if everything that will happen already exists in the space-time structure, then what happens to free will? To choice? To the feeling that what you do right now genuinely matters? I think the honest answer is complicated. And I'm not going to pretend it's simple. The block universe does not obviously destroy free will in the way people fear. Your choices are part of the four-dimensional structure. They exist. They have effects. The fact that those effects are already encoded in the space-time structure doesn't make them less real or less yours. Your deliberation, your values, your reasons, these are causally active parts of the structure. The output of your decision process is part of what determines what gets written into the space-time record. What the block universe does challenge is a particular picture of free will, the picture where you stand outside the causal order and make choices that are not themselves caused by anything. That picture was always philosophically problematic. Physics just makes the problem harder to ignore. What retrocausality challenges is different and deeper. If the future can influence the past, then what you will choose tomorrow is already causally active today in ways you can't access consciously. Your future self is reaching back through quantum processes you can't feel or control, shaping what appears to be your present deliberation. Think about what that means. The feeling of deliberation, the experience of weighing options, considering consequences, arriving at a decision may itself be partly shaped by what you will decide. Not predetermined in a crude clockwork sense, but influenced, touched by the future in ways that bypass your conscious awareness entirely. That is a genuinely strange idea. I won't pretend otherwise. But here is what I find most striking about this whole picture. The neuroscience points in the same direction. In the 1980s, Benjamin Libet performed experiments that shook the philosophy of mind. He asked subjects to flex their wrist whenever they felt like it, noting a clock position at the moment they felt the urge to move. Meanwhile, he measured brain activity throughout. The result? The brain showed measurable electrical buildup, the readiness potential about 550 milliseconds before movement. But subjects reported feeling the conscious urge to move only about 200 milliseconds before it. The brain had committed to the action more than a third of a second before the person felt they had decided. The decision happened before the awareness of deciding. Libet's experiments are contested. The interpretation is debated, but they point in the same direction as the quantum results. The causal story we tell ourselves, I deliberated, I decided, I acted, may be a reconstruction. A narrative imposed on a process already underway before the narrative began. Causality, as we experience it, may be the story consciousness tells about a process that doesn't actually work that way at the physical level. But here's what I find most remarkable about all of this. The fact that we can ask these questions at all. The fact that physics has advanced to the point where causality, the most fundamental assumption in all of science, is itself a subject of serious empirical investigation. For most of human history, cause preceding effect was not an assumption. It was invisible, so obvious it didn't need to be stated. The water we swam in, now we have experiments that challenge it, interpretations of quantum mechanics that work better without it, a deep theory of space-time that makes the past and future equally real, a neuroscience that suggests even the experience of deciding may arrive after the decision has already been made. We are not just learning new facts about the universe. We are discovering that the categories we use to organize those facts before and after, cause and effect, past and future, may not carve nature at its joints. They may be tools, useful, powerful, extraordinarily reliable tools for navigating the world we experience at human scales, but not the ultimate structure of reality. The universe does not have a preferred direction of causation built into its foundations. We gave it one. Because we had to. Because we're the kind of beings that experience time flowing forward, that remember the past and not the future, that have built every experiment, every theory, every story about the world on the assumption that causes come first. The universe was under no obligation to cooperate with that assumption, and the evidence is increasingly suggesting it doesn't. Think about that the next time you make a decision, the next time you trace an effect back to its cause, the next time you assume that what happens now could not possibly have been shaped by what hasn't happened yet. The universe is stranger than that. It always has been. We're only now beginning to see how